Good morning. Today we are going to see problems on dual cycle. So let's discuss about the problems on dual cycle. In previous class, we discussed how to derive an expression of efficiency, work done calculation, and mean effective pressure for dual cycle. So based on that, we are going to see some problems. So first, you can note down the question and air standard dual cycle has a compression ratio of 16 and compression process begins at 1 bar, comma 50 degrees Celsius, where the maximum amount of pressure is 70 bar. The heat transfer to air at constant pressure, which is equal to that at constant volume. By using this parameter, we need to estimate the following parameters: the pressure and temperature at all cardinal points of the cycle. So next parameter, we need to measure the cycle efficiency and one more parameter is mean effective pressure. Mean effective pressure. So just consider the CV value is 0.718 kilojoule per kg Kelvin and CP value is 0.005 kilojoule per kg Kelvin. Fine. So these are the data given to us. Then we can measure pressure and temperature at all the points of the cycle and cycle efficiency, mean effective pressure. So first of all, please note down the given data. Given is the air standard dual cycle has a compression ratio of 16. Already we know that the symbol for compression ratio is denoted by the symbol R, so which is 16. and the compression process begins, right? Compressor process begins at 1 bar. So we know that where the compression process begins. So before that, please you can plot PV diagram of dual cycle. So that is pressure volume diagram. We know that already we discussed it in dual cycle derivation itself. So initially, which is adiabatic reversible compression process, then heat addition takes place at partial amount of constant volume, and another partial amount will be a constant pressure. And again, there is a adiabatic reversible expansion process where the pressure getting increases. Finally, at constant volume, the heat rejection takes place. Okay. 1, 2, 3, 4, 5. Just we are giving the names to that. So the process between 1 and 2 and 4 and 5, which is a reversible adiabatic process. 5 and 1, which is a constant volume. So where heat rejection takes place between the process 3 and 4 and 3 and 2, the heat supply takes place. Right. So the compression process begins at the initial point 1. So pressure 1 is given 1 bar and temperature also given at the compression begin state where the cardinal point is T1, which is 50 degrees Celsius. So you can convert in terms of Kelvin. So we can get us 323 Kelvin. Okay. And the maximum pressure is 70 bar, right? So maximum pressure, please look at the PV diagram where the maximum pressure is raised, maybe the point 3 or zero point 0.4. So actually, which is a constant pressure process, so definitely P3 which is equal to P4. So we can maximum pressure may be achieved at the point P3, P4, which is 70 bar. Okay. Then apart from this, heat transferred to the air at a constant pressure and which is equal to constant volume. Right. So just a condition is given. Heat supplied at a constant volume which is equal to heat supplied at a constant pressure. Okay. Then these are the data given to us. By using that, we need to measure such parameter. Okay, right. So now go to the solution part. The first we need to consider the various pressure points and temperature point, right? So actually P1 and T1 is given and P3, P4 is given. The pressure we need to measure P2 and P5. Okay. Like that, temperature T1 is given. So rest of the parameter T2, T3, T4, T5 we should measure. Okay. Right. So just considering the process between 1 and 2. So which is a reversible adiabatic compression process. So the general equation P1 V1 power gamma equal to P2 V2 power gamma, right? So here we know the P1 pressure and compression ratio is given. Compression ratio is nothing but V1 by V2. So just you can rearrange the equation P2 which is equal to P1 into V1 divided by V2 whole power gamma. Okay. And P1 is 1 bar. So just to substitute the value, and R value is nothing but 16. Our gamma is not given, so specific gamma value for R air is 1.4. So P2 is, we can get around 85.5 bar. Then like that we can measure T2. Right? So already you know the relation. Again you can use the same equation. Uh, instead of PV relation, you go for the T and V relation. Right? You can form T and V relation from the process 1 and 2. So we can form the equation like this: T2 into T1 into V1 divided by V2 whole power gamma minus 1. So actually T1 is known value, T2 is the unknown value. T1 given is around 323 Kelvin, and V1 by V2 is nothing but R. The R value is 16 and 1.4 minus 1. So if you substitute those parameters, means we get the T2 value is around 979.15 Kelvin. Okay. So you can use a calculator to measure these parameters, right? P2 and T2 is calculated. Then you can go for the S parameter. Just you can consider the process 213. 213 is a constant volume process. So P2 V2 divided by T2, which is equal to P3 V3 divided by T3. Because of constant volume process, both the term get cancelled because of V2 equal to V3. Okay. So from that you can measure T3. Right? T3 is unknown parameter and P3 value is given to us, and P2 is measured, T2 also measured. Right? So what is the P3? P3 is around 70 bar and P2 is 48.5 bar, and T2 value is around 979.15 in terms of Kelvin. Right? And we get the T3 value is around 1413.20 Kelvin. Then likewise you need to measure another coordinate points, right? So next you need to measure T4 and T5 and P5 also, right? So if you're considering the process between 4 and 5, right? So actually you know the value for P4, but you don't know the any parameter of T4 and T5. So you are not measure the T4 and T5 parameter if you're using this relation like that. So that the condition is given, right? The heat transfer, right? So between, you can consider the process 2 and 3. Okay. So the general formula, you know that MC, which is a process takes place between 2 and 3, which is a constant volume. So T3 minus T2. So here mass is not given, so you can consider as a per kg, and CV value is given, which is 0.178, and T3 value is 1413.20, and T2 is 971, sorry, 979.15 Kelvin. Okay, and you get the answer is around 31164 kilojoule per kg. This is heat supplied at constant volume process. So our condition given, right? What is that? Heat supplied, whatever takes place at a constant volume, which is equal to heat supplied between the process 3 and 4, that is constant pressure process also. So that again you can consider the between 3 and 4, which is constant pressure T4 minus T3, which value is given for a CP 1.005, and T4 is unknown parameter, that is we need to measure, and T3 is 1413.20. Q34, which is actual condition is given, so you have to consider, which is equal to 31164. So from that you can measure what is T4. So if you measured means you can get around 1723.28 Kelvin. Okay, so this is T4. And again we need to measure another parameter. So that is T4, sorry, T5 and P5. So you have to considering the process between 4 and 5. From that you can measure P5 and T5. So the process between 4 and 5, which is nothing but a adiabatic reversible expansion process. So P4 V4 power gamma equal to P5 V5 power gamma. Just you can rearrange the equation in terms of T and V relation. T and V relation. You can get like this. T5 divided by T4, which is equal to V4 divided by V5 whole power gamma minus 1. I hope all of you know how the relation arises here. Suppose if you have doubt, please refer the previous class derivation. Okay. And here, actually T4 is known value, T5 is unknown value. And what about the V4 and V5? So for this also some relations we discussed in previous class. So once again I repeat here, you can see here. How can you measure V4 by, sorry, V4 by V5? So before that, see, V5 by V4, like this relation we can form. Actually we get the R power, R divided by rho power gamma like that. So you can refer the PV diagram, V5 which is nothing but which is equal to V1, right? V1 divided by V4. Just multiplying with the factor and dividing by the term V2, you get V1 by V2, which is nothing but R, and get V2 divided by V3, sorry, V4. And V2, which is equal to V3 because of constant volume process between process 2 and 3. So R into V3 divided by V4. And what we'll do for the V3 divided by V4? Again, we need to, V3 divided by V4 is nothing but cutoff ratio So actually cutoff ratio is V4 by V3 in dual cycle. So you can form or you can measure the V4 by V3, V4 by V3. So you have to considering the process between 3 and 4, right? So 3 and 4 is nothing but constant pressure process. So P3 divided by T3 equal to P4 V4 divided by T4. Here constant pressure P3 equal to P4 get cancelled and remaining time is here T4 divided by T3 which is equal to V4 divided by V3, right? And we know the value for T4 and T3, right? The T4 value is measured 1723.28 divided by T3 also measured which is 1413.20 which is equal to V4 by V3. So then you can get V4 by V3 which is nothing but the rho cutoff ratio which is equal to 1.219. Okay. Now see here instead of this one actually V4 by V3 is measured here V3 by V4 just you can say like this. Okay, and R value is known value which is 16 and rho value is 1.219, right? So you get V5 by V4 which is equal to around 13.1. Right? So actually for there is no need to derive every in every problems about these relations. If you have remain means directly you can use because already we discussed in the derivation part itself. So there is no need to solve in every problem, right? Then, so here T5 divided by T4 which is equal to V4 divided by V5 gamma minus 1. So here, actually here V4 by V4, we measured for a V5 by V4. So 1 divided by 13.1 whole power 0.4, right? 1.4 minus 1 we can directly write as 0.4. And you know the T4 value, right? So T5 and T4 value is around 1723.28 into 1 divided by 13.1.4 and finally T5 is given as 615.81 Kelvin. So this is T5 and one more parameter we need to measure which is P5, right? So again we need to consider the process between phi and 1. Phi and 1 is a adiabatic, sorry, constant volume process at heat rejection, right? So constant P5 V5 divided by T5 equal to P1 V1 divided by T1. So since constant volume process P1 and P5 V5 get cancelled, actually P5 is unknown parameter P1 into T5 divided by T1. P1 is 1 bar and T5 is 615.81 and T1 is 3 323 Kelvin and P5 is 1.90 bar, right? Okay, fine. So all the parameters, that mean all the cardinal points of pressure and temperature is measured. So finally, pressure and temperature at all points. So where P1 is 1 bar, P2 is 48.5 bar. P3 is given, which is a 70 bar. So since constant pressure passes takes place between 3 and 4, P4 also 70 bar, and P5 is 1.90 bar, right? So because of pressure reduction here, so there is a thing. Likewise, temperature T1 is given 323 Kelvin, T2 is measured around 979.15 Kelvin, and T3 is 1413.20 Kelvin, T4, which is also measured thing, 1723.28 Kelvin, and finally T5 is 615.81 Kelvin. Right. So apart from this, again we need to measure two more parameters, that is the cycle efficiency and mean effective pressure. Okay. See here. So next parameter is cycle efficiency. We know that the general formula for measuring efficiency is nothing but work done divided by heat supplied. Actually, you don't know the work done value. So we can say work done is nothing but the difference between heat supplied and heat rejection. So from this you can simplify the equation like this: QR divided by QS. So we know that value for all the temperatures, right? So easily you can measure the heat supplied and heat rejection. Else you can go for the simplified equation in terms of cutoff ratio, compression ratio, and pressure ratio, but we don't know the pressure ratio. Pressure ratio also we can measure because we know all the pressure points P3 by P2. So any one of the formula you can use to measure the cycle efficiency. Here I am using the 1 minus QR divided by QS. Okay. So QR is MCV T5 minus T1. QS actually takes place at two positions, so you can use both the thing MCV T3 minus T2 plus MCP T4 minus T3, right? So just you can omit the masses because of the kg, right? And we substitute 1 minus 0.718. T5 is around 615.81 minus T1 is 323 divided by CV is 0.718 into T3 is T3 T3 is 101413 minus T2 is 979.15 plus CP is 1.005 into T4 is 1723.28 minus of T3 is 101413.30, right? So else you can use, already we measured the heat supplied at a constant pressure and constant volume, right? Which is around 331. So you can directly use the value also here, no problem. So if you substitute these parameters means you get around 0.663. So the cycle efficiency of dual is approximately 66.3 percentage. Okay, and next parameter is we need to measure mean effective pressure. The general formula for measuring mean effective pressure is nothing but work done by V1 minus V2. So how can you measure work done? Cycle efficiency is nothing but work done divided by heat supplied, right? So you know the cycle efficiency and heat supplied. From that you have to measure work done. Cycle efficiency is around 66 percentage, and heat supplied is actually you need to consider the sum of heat supplied at a constant pressure and constant volume. It's get around 311.64, right? So we get around 323, and where the work done is 413.23 kilojoule per kg. This is work done. Okay, and so work done is 413.23. So taking commonly outside the term V1 here, so you get 1 minus V2 by V1. So else you can measure V1. How can you measure V1? Again P1 V1 equal to or P1. So you know P1 V1 or sorry, we know P1 or T1. So from that measure the T1 or is 0.287 kilojoule per kg Kelvin, into T is 323 Kelvin, and which is a 1 bar. So you please convert in terms of kilonewton per meter square, 1 into 10 power 2. Here the unit is kilojoule per kg Kelvin into Kelvin. So Kelvin, Kelvin get cancelled. Newton, joule you can say as a Newton meter. So kilonewton get cancelled. Meter square get cancelled. Sorry, meter cube we can say as meter. If it goes numerator means we can say as meter cube per kg, and V1 value is around 0.927. And how can you measure a V2? So the compression ratio is nothing but V1 by V2, right? So 16 equal to V1 value is 0.927. So from this you can measure V2. Okay. So V2 is 0.927 divided by 16. This you can substitute here, and the mean effective pressure is 413.23, and V1 is 0.927 minus of V2 is 0.0057. If you use these values, finally you can get around 476 kilonewton per meter square. So we can say in terms of bar means we can say 4.76 bar. So this is the mean effective pressure of the cycle. Thank you.